In this video, I introduce a stochastic neighbor embedding for high-dimensional data visualization. Stochastic neighbor embedding converts the Euclidean distance between two data points in high-dimensional space into the conditional probability of similarity, which can be viewed as a dimensionality reduction technique, so that we can visualize the results generated in high-dimensional space. For each object I and each potential neighbor j, its metric probability Pij is computed, which is interpreted as a probability of I picking j as his neighbor. The similarities D is a scaled squared Euclidean distance between data points xi and xj in high-dimensional space, where sigma is selected to make entropy of a distribution over neighbors equal to log k, where k is the effective number of local neighbors. For nearby point xj, Pij is high and is low otherwise. In low-dimensional space, Gaussian neighborhoods use a fixed variance 1/2 so that the induced probability Qij of data point I picking data point j as its neighbor is a function of low-dimensional images Yj of all objects, which is given by here. SNE tries to match Pij and Qij by minimizing a sum of KL divergence between Pij and Qij distributions over neighbors for each object here. KL divergence is asymmetric. The gradient of the loss C with respect to Y is computed by this formulation, which means that a sum of forces pulling Yi toward Yj or pushing it away depends on whether j is observed to be a neighbor more or less often than desired. If Pij is the same as Pji and Qij is equal to Qji for any I and j, SNE is symmetric and his loss function is defined as here. In symmetric SNE, the similarity of Qij in low-dimensional space is defined here, and the similarity in high-dimensional space is defined here. Similarly, the gradient of loss function C with respect to Y is computed by this formulation. The metric SNE has an equal or better performance than SNE. For more details, please check with these references. Thank you. Bye.